Hello, my name is Gregory Kimball and I work at SunPower Corporation. Today I'd like to talk about synthesis of multi-year PV production data using generative adversarial networks. I worked on this project with Camille, Pauchet, Rasoul, Ghadami, Alberto, Zaragoza, and others working on the team. So synthesizing multi-year PV production data. Why would we want to do that? Well, solar resource is variable from year to year, from day to day, and this variability in solar resource affects PV production, and PV production affects project economics. So we care a lot about the patterns of PV production and what they're likely to be in the future. So if we want to synthesize some PV production data that's never been seen before based on historical observations, you can either use rule-based methods where you've got a series of functions to synthesize data, or you can use machine learning methods such as generative adversarial networks to create a wide diversity of PV production data for your forecasting. But whenever you're synthesizing data, you need to make sure you're evaluating it carefully. So in this talk, we're going to focus on annual, monthly installation statistics, as well as the application to a demand charge management simulation where we've got PV systems and batteries working together to manage customer load. So installation in the United States. Just to talk about annual values for a bit, the map in the middle here shows the 1 sigma standard deviation of annual installation values in the United States. You can see that across most of the country, variability is between about 2 to 4%. Also in the desert Southwest is where the year-to-year behavior is most stable, getting down to around 1% interannual insolation. And then I've highlighted a few locations here: Fresno, Phoenix, Boston. What these plots represent is 1 year of insolation data, starting at the top January 1st, going down to December 31st. So you can see the brighter yellow in the middle reflects the summer, followed by the darker top and bottom reflecting the winter. And then throughout the year, you can see weather patterns show up as red and darker spots. So the rule-based method we developed follows this sort of schematic here, where the input is a 15-minute 1-year time series file, and then there's also a latitude-longitude input. So the latitude-longitude input determines what the annual target will be when we're making a new variant. It will be higher or lower on an annual basis based on the map that I showed on the previous slide. And we also take this input data and shuffle the days around. This is basically just copying groups of days over other nearby days. The last step is to copy days in a way that meets the annual target that we set based on the location. And this is by copying higher insolation days over low and vice versa. Now the result of this is a wide set of output data files, basically as many as you want, and they're only determined by the random seed that goes into the algorithm. So I've got some examples here on the right showing data that was not changed by the method, data that was swapped, and data that was modified to meet the annual target. And these are all variants that we could use. Now we can also use machine learning methods like generative adversarial networks. So let me say a little bit about the way those networks work. When you train a GAN, you start with a generator model and a discriminator model that are trained in conjunction. The discriminator model tries to correctly identify real data from an actual source, from your reference source, versus fake data that's generated by another network. And you train it to minimize its error in making this assessment. And then you've got a generator model that takes random inputs called the latent space inputs of what you're trying to simulate, and then outputs fake data to be later studied by the discriminator. So yeah, you can use the generator data directly for whatever application you want, but when you're training it, you use a loss function that makes the generator benefit from having successfully fooled the discriminator and having its fake data marked as real. So for the problem we're trying to solve, we don't just want any old random weather file. We want it to be conditioned on a location. So this is called a conditional GAN architecture. And in this case, the orange Y bubble represents the location. So the generator, you give it random numbers for a location, and then it gives you an output. You tell the discriminator which location this is, and it'll tell you if it thinks it's real or fake. So for our case, the way we use the generator is we're giving it 50 random numbers plus the latitude and longitude, and it's outputting daily production or insolation values, so 365. And we call this intermediate output GAN. But if you want to process it into 15-minute data, that's where we use the 15-minute reference file that's provided. And this, we do a matching process of the days of the raw output to the 15-minute input, and that gives us the outputs that we want. And you can see we can run this as many times as we want with different random numbers to get different PV production forecasts. So let's inspect some of these examples. So in this plot, the first row is NSRDB. This is historical ground station measured insolation. And then I've run the V2 rules-based method and the GAN-M machine learning method using to generate insolation data as well. The first row is Fresno, followed by Boston and Arizona. Each of these plots represent 1 year of daily insolation values. And you can see that in general, the seasonality, the behavior in the summer versus the winter, the pattern and duration of cloud cover and other weather patterns, it's pretty consistent across these methods. So by inspection, the data looks pretty plausible, I would say. But we should go a little deeper than that. So the first thing is we can look at a whole bunch of years together. We don't have to just look at one example. And in the plots on the left, I'm showing 29 years of NSRDB historical data. In this case, each row represents 1 year, and then where you are on the x-axis is the day of the year. When you compare the historical NSRDB data to V2, you can see that V2 is maintaining a few too many characteristics across multiple runs. So for multiple years, we'll get the same weather patterns on the same days with some frequency. And this is not perfect. This is not really what we want. So, but it's kind of hard to address with a single input. The nice thing about the GAN-M method is that most of the correlation from 1 year to the next is gone, looking more like historical data. And we're also maintaining the seasonality and the clear periods as we would expect. So even multiple years of inspection looks good, but let's talk about a few statistics. When it comes to annual insolation, you can see that the NSRDB, the V2, and the GAN-M methods are all pretty close to the same 2100 kilowatt hours per meter squared. So this is a great benchmark to start off with. And then when we look at monthly insolation, this is mean monthly insolation from January to December. You can see that all the models are following the right shape. The last statistic is monthly variability. So for each month you take the daily values and you can compute the standard deviation, then average them across all the runs. So in this case, you can see that the rules-based methods are a little bit low, something like 2 to 5%. In the daily variability for each month, but the NSRDB and the GAN data is more reflecting the full 8% level of variability in the winter versus the lower 3 to 5% in the summer. So when we go into a clustering analysis, what you'd want to see in a clustering analysis is that the data mostly overlaps. If the clustering tool can separate the fake versus the real data, that would be a bad sign. So we find pretty good overlap between the rule-based machine learning and ground station data, although the rule-based has a little bit lower extent, reflecting some of the lower diversity that we were concerned with. Now, the main application for this data is in demand charge management simulations. So for these kind of systems, we've got a customer load and a solar array and a battery behind the meter, and we're trying to manage the net load that's presented to the grid. And the sort of behavior that a system like this tries to do is you can see in the plot on the right here. And what this one thing this plot shows is the solar production in orange, followed by the battery dispatch in the dark blue and the light blue. You can see in the morning we're doing a dispatch, discharging the battery to reduce the customer load. And then we're charging it for the whole morning in the lighter blue area, and then doing another discharge in the afternoon. So to be able to optimize this behavior, you need to, it's impacted by the PV production. So when you're designing this controller, you want to study a wide range of solar conditions and make sure that your algorithm can cover all of them. So for the last analysis, this is a savings analysis for generated data from each of these methods, and with an NSRDB reference where we're trying to estimate for these historical years what would savings had been. The first thing that comes out is a good separation between location, where the Phoenix results are higher than the Fresno, are higher than Boston, as you would expect based on the solar resource for these different locations. And also the variability is pretty good, where the cluster size is about the same for each of these methods, if maybe a little lower for V1 than V2. So in summary, the class of methods we're talking about today, they receive an input for a single year. In this case, we're doing an irradiance simulation for Boston based on 1974. The output is as many variants as you want of 15-minute irradiance data. For this example in Boston, you can see the historical data reference on the left, the V2 method in the middle, and GAN-M on the right. And as you can see, these methods generate plausible data that can be used in a wide set of applications. Thank you for your time.